All right, welcome back. So now what we're going to do is practice evaluating the trigonometric functions. Not when we're given a triangle, but we're actually already given a trigonometric ratio. And basically, remember the trigonometric functions, right? These comparisons are comparisons of sides of a triangle. So if we're not given a triangle, the first thing I tell students to do is to sketch a triangle. So if I have cosine of theta equals 3 over 5, again, we need to understand that. What is the cosine of an angle? Well, again, that is adjacent over hypotenuse. So what I'm going to do is I'm just going to draw a triangle, a right triangle, by the way, right? And again, where does theta going to go? Well, it doesn't really matter. If you want to put theta here, that's fine. So here's going to be your hypotenuse, which we said was 5. And then here's going to be your adjacent side, which is 3. Remember, the adjacent is between your theta and your 90 degree. Now we need to figure out what our opposite side is. Now, what's helpful here is hopefully you recognize that this is one of those Pythagorean triples. So if I recognize this to be a Pythagorean triple, you could do the Pythagorean theorem, but for us to save some time, I'm just going to write this in as 4 because I recognize this Pythagorean theorem relationship. So now let's go through the 6 trigonometric functions. So the first one is going to be the sine of theta. Again, that's opposite over hypotenuse, so that's going to be a 4/5. We have the tangent of theta, which that's going to be opposite over adjacent, so that'd be 4/3. And the nice thing I can do here is rather than going through the reciprocal relationships, I remember that, all right, well, cosine of theta, that was already given to me, right? So that's 3 over 5. I can now find the reciprocal relationships just by taking the reciprocal of the sine, cosine, and tangent. So I could say the cosecant of theta is going to be 5 over 4. The cotangent of theta, that's going to equal 3 over 4. And the secant of theta is equal to 5 over 3. So you can see how this Pythagorean triples really makes things a lot easier. So now let's get into another one. You can see I'm using a different variable here, alpha. So I have tangent of alpha is equal to 3/2. So again, let's draw the right triangle. Now, where do we want alpha to be? Well, let's just put alpha in the same place. I mean, why not? There's nothing wrong with it here. We know that here's the right triangle. Now the tangent is opposite over adjacent. So that's going to be your opposite side. That's going to be your adjacent. Now in this case, I don't know what the hypotenuse is. So let's call the hypotenuse C if you want to. And then we can use the Pythagorean theorem. So that's 2 squared plus 3 squared equals C squared. All right, now in this case, we're going to want to simplify our radicals if we can. All right, so in this case, we have 2 squared, which is going to be 4. Plus a 3 squared, which is 9, equals C squared. So therefore 13 equals C squared. So C is going to be the square root of 13. Now I can't simplify the square root of 13 anymore. So therefore I will just leave it as the square root of 13. All right, so that's going to be our hypotenuse. So when we go through the sine now, I'll say the sine of alpha, sorry, not theta. Sine of alpha is going to be 3 over the square root of 13. Now, a lot of times in for our trigonometric functions, we are going to simplify this by rationalizing the denominator. So again, we don't want to be dividing by a square root. So what I can do here is multiply by the square root of 13 on the top and the bottom. What that does is that gives me a 3 square root of 13 all over. Now, square root of 13 times square root of 13 is just going to be 13. But now at least I have an example where my denominator is not a irrational number. So therefore you can see it's 3 square root of 13 to 3. So this is just a very common practice for the trig. So a lot of times, unless you're not asked to do it, it's typically answers on like tests and exams are going to have a rationalized denominator. So, and that's just kind of your accepted form. So cosine of theta is going to be 2 square root of 13. And we're going to get pretty good at this. When you rationalize the denominator, hopefully you get the square root of 13, right? I don't really even need to show my work. I have the tangent of alpha is 3 over 2. And then let's go through my reciprocals. Now, the nice thing about the reciprocal identities here is when I'm doing my reciprocal identities, I don't really need to, you don't want to invert this because then you're going to have a square root again in the denominator. So just take the reciprocal of your original ratio. So this is going to be the square root of 13 over 3. Or, yeah, right, it's opposite over adjacent. Then you could do the secant of alpha. That's going to be adjacent over hypotenuse. I think I said that wrong last time. Hypotenuse over opposite. So this one is adjacent over, hypotenuse over adjacent. I'm speaking wrong. Gotta be careful. Slow down. So opposite over adjacent. And then we have the good old cotangent of alpha, which is going to be just the reciprocal of tangent. So that's going to be 2/3. Okay. The next one is going to be the sine of beta. So in this case, again, we know that this can be opposite over adjacent. So again, we can create another angle. Now again, like I'm just being kind of consistent. Not all the triangles are going to look like this, but sometimes, you know, you can just see that that sometimes just makes things a little bit easier for that. So here we're going to have beta. This is going to be the square root of 3, and this is going to be 2. Now, you might recognize this is a 30, 60, 90 relationship. You might not. If you remember that 30, 60 degree, 30, 60, 90 triangle had the square root of 3 on it. And so therefore, what you would have is the relationship between the two legs was the one leg. And again, we don't know if that's the long leg or this is the short leg because this is actually the long leg in this case. But you remember from one leg to the next, all you had to do was multiply by the square root of 3. So if I had to divide by the square root of 3 here, then I would get a 1. And then if you multiply that by 2, you would get, you multiply by 2, you get the hypotenuse. And that is actually the relationship there. If you were to do the Pythagorean, again, you could do the Pythagorean theorem if you want to. So let's just call this x, squared plus the square root of 3 squared equals 2 squared. I'm just recognizing this Pythagorean or this 30, 60, 90 triangle because that's why we want to cover those 45, 45, 90 triangles. It just makes your, it's going to make your life a lot easier when you can see these relationships. So there you go. So again, you could have done Pythagorean theorem, and most students, especially at this stage, are not going to recognize that relationship. I'm just trying to give you a little bit of tips and seeing that relationship there. So we have sine of beta. So let's just rewrite that. Sine of beta equals the square root of 3 over 2. Then we have the cosine of beta. That's going to be the adjacent over hypotenuse. So that's 1/2. We have the tangent of beta, which is going to be opposite over adjacent. So that's going to be square root of 3 over 1, which is just the square root of 3. Then let's go look into our reciprocal relationship. So we have cosecant of beta, which is going to be hypotenuse over opposite. And again, we have a radical in the denominator. So again, I'll rationalize this denominator for you. And you can see that's going to be a 2 square root of 3. Square root of 3 times square root of 3 is just going to be 3. The secant of beta is going to be 2 over 1, which just gets simplified to 2. And then we have the cotangent of beta, which is going to be a 1 over the square root of 3, which again, rationalize the denominator. Since we're doing these all for the first time, I'll kind of work through my way through them. So that's going to be square root of 3 over 3. All right, so let's get on to the next example. So in secant of x equals 3, remember our trigonometric relations, guys, are comparisons, right? We're comparing how big is one length compared to another length of a right triangle. And if you just have an integer like 3, like what is the comparison? What are you comparing what to what? So what we want to do is we want to be able to write this as a fraction. So how can you write 3 as a fraction? Well, remember, we can always write a number over 1. So now you can see that the hypotenuse, right? Because secant is hypotenuse over adjacent. So how big is the hypotenuse compared to the adjacent side? And you can see that this ratio is going to be 3 to 1. Now, I don't recognize this to be a 30, 60, or 45, 45, 90 degree ratio, nor a Pythagorean triple. So I'm just going to default then going back to my Pythagorean theorem. So in this case, I have my hypotenuse. So it's going to be 3 squared equals, let's draw a triangle first. So I'm going to draw a triangle. Again, I'll just draw the same triangle, keep myself very consistent here. All right, so I have the hypotenuse and I have my adjacent side. So let's call this x this time. All right, so I know that 1 squared plus x squared equals 3 squared. And therefore I have 1 plus x squared equals 9. Subtract 1, x squared equals 8. And now when I take the square root, I have something I can actually simplify as a radical. So x equals the square root of 8, right? But again, we want to use the simplified version here. So what we want to do is break this down into what is a square number that, or what is a number that, a square number that evenly divides into 8. Well, we can break this up into 4 times 2, right? So the square root of 4 is 2. That means we can take it outside of the radical and rewrite this as 2 square root of 2. And that's going to become very helpful because a lot of times the problems that we'll be dealing with in this chapter are going to be radicals that have been simplified. So if I know secant of x equals 3 over 1, well, that can make my cosine of x be pretty simple. That's just going to be 1/3, right? It's just the reciprocal relationship. Then we can do the sine of x. Oh, that was a bad way to use x, right? Shouldn't have done that. I should have used like c. Let's just rewrite that so other people don't, dang it. Or not use c, let's use a or something so other people don't get confused later on. Let's call that a squared, a squared. So when I have this on my notes downloaded, people will, because x represents the variable, or x represents the angle in this problem. So I don't want to like overly confuse people here. So therefore that's 2 square root of 2. Okay, so sine is going to be opposite over hypotenuse. So that's going to be 2 square root of 2 over 3. Nothing I can really simplify here. But again, if you do have one of those problems, always try to simplify the fraction if you can. The next one is let's just do the reciprocal relationship here. So the reciprocal relationship is going to be 3, 2 square root of 2. And if we rationalize the denominator, that's going to give us a 3 square root of 2. 2 square root of 2, or square root of 2 times square root of 2 is 2, times 2 is 4. Okay, and then we have cosine, we have secant. All right, let me just write in secant. So that's just going to be 3, right? Then we have the tangent. I want to do tangent first. So tangent of x is going to be, that's going to be 2 square root of 2 over 1. So that's just 2 square root of 2. And then we have the cotangent of x, which is 1 over 2 square root of 2. So now when I go ahead and rationalize the denominator, I get the square root of 2 over 2 times square root of 2 times square root of 2 is 2 times 2 is 4. Okay, so there you go, ladies and gentlemen. That is it for identifying the 6 trigonometric functions of a triangle. Again, you look for those Pythagorean triples as well as the 30, the special right triangles, and you'll be on your way. You'll probably need to, practice a little bit the ratios for the 6 trigonometric functions, but throughout this chapter, we're going to be doing this for the rest of the time, so you'll get very, very used to it. But that is it. Go ahead now and work on the quick quiz, and I'll see you in the next section. Cheers.